look at solutions. So again, solutions is really a lot of just more intermolecular forces, right? So it's just more intermolecular forces when we're doing solutions. And then we're going to talk about colligative properties. So great review for your quiz. What intermolecular forces exist between the molecules of ethanol? Let's see here. This is OH, that's carbon. This is O, carbon, carbon, carbon. These are all hydrogens. Okay, so this is a great for your exam, great for your quiz, right? So the intermolecular forces that exist between here, right? So we've got this OH here, right? So we've got hydrogen bonding. And remember, everything has LDF. LDF is going to be weaker because it's hydrogen bonding, right? So everything has the dispersion forces. And the question is next one, which intermolecular forces are in this one? Now this one does not have hydrogen bonding, but it does have dipole-dipole, right? So dipole-dipole, and of course LDF, because everything is LDF. So one of these compounds is a liquid at room temperature, and the other is a gas. All right, here's my question. Which one is a liquid and which one is a gas? So 1 or 2. So just feel free to type it in the chat. Yes, you can send it to me direct, which I've seen a few of those already. So which one's a liquid, which one's a gas? Yes, this one is our liquid. Yeah, stronger intermolecular forces, likely to be a liquid at room temperature, right? So these are great questions, again, for your exam and for your quiz. Just a little review on intermolecular forces. Okay, so what are we going to talk about with solutions? So some of you may have seen some of these before, but a lot of you haven't. So we're going to be talking about osmosis, osmotic pressure, vapor pressure, volatile solutions, and then we're going to talk about really fun things like colligative property and Henry's law and solubility of gases. So that's kind of the last piece of what we're going to talk about. Okay, so we know that you're not supposed to drink ocean water, right? And like when people are like shipwrecked or whatever, they're always like, don't drink the water, don't drink the water. Well, what we're going to talk about now is, well, why can't you drink the water, right? And it has to do with the difference in the salinity of the ocean water and the salinity in our red blood cells. And so what happens is there's more salt in the ocean water than there is in our body, right? A higher salt. And so what happens is our red blood cells want to have the same amount of water on the inside as the outside. They like to be in equilibrium or the same. But ocean water has more salt than water. So the water, what happens is it leaves the red blood cells trying to equalize the amount of water on both sides. And then they dehydrate and then we die, right? So when you immerse them in seawater, the red blood cells dehydrate, right? And they shrivel up. So too high of concentration of ions means too low of concentration of water. And so the difference in the water concentration results in a migration of the water molecules from the cells to the outsides of the cells. And this causes them to shrivel and collapse and dehydrate. And this is because the membranes of the red blood cells are semi-permeable, meaning that there's ways that the water can go in and out of the cells, but the salt molecules can't go in and out of the cells. So if we ever have a semi-permeable membrane, water is the only thing that can travel in and out, and it can migrate in and out. And again, water wants to be the same on the inside as it is on the outside, the same concentration. This is osmosis. So the water is always going to move from a high concentration water or a low concentration of solute to a high concentration water to a low concentration water. It wants to be the same. Okay, so let's look at let's look at that in pictures. I think it's easier in pictures. Okay, so we have 3 solutions. Hypertonic, isotonic, and hypotonic. So those of you who have like taken any kind of like biology classes, you've probably talked about those. So hypertonic, that is one in which the solution concentration is higher on the outside than is on the inside. So remember, if the water wants to be the same water concentration on both sides. And so if there's a higher concentration of salt on the outside, the water's like, oh, that's too much salt. We must go out. We must go out. Us as water molecules must go out to decrease the concentration of salt on the outside. That's what happens when you drink seawater. Same thing that happens when you get dehydrated, right? So when we get dehydrated, and you're like so thirsty, right? What happens is the amount of, I'm just going to put pluses and minuses, the amount of salts out here is too high. There's too many salts out here. And the water's like, oh, that means there's not enough water. So we need to put more water molecules out here. And so the water molecules will leave the cells to try and increase the amount of water molecules. And then you get dehydrated, right? And then you end up in the hospital, very bad. That's why you got to drink water, because we need to make sure that the amount of water on the outside of the cell is the same as the water on the inside of the cell. Now, this is very dangerous. This is also very dangerous. And people have actually died. There was a radio contest, it was probably before you were born, and so it was like you can win a car depending on who can drink the most water in the shortest amount of time, and like somebody died doing it. Now, how did that happen? If there's too much water, so these are going to be water molecules, because water molecules look like this, right? So I'm just going to do that. That's a water molecule. If there's too much water molecules on the outside of the cell, then the cell's like, oh, there's too many water molecules out here and there's more salt molecules in here. We need the concentration to be the same. So water molecules come in here to dilute the amount of salt, because there's barely any salt here compared to the amount of water. And so the water molecules will actually come into the cell to try and make the concentration the same, and then they blow up. Yeah, very dangerous. By the way, you have to drink like 10 gallons in an hour or something. So it's like you drinking a gallon of water is not going to kill you. But you can drink. There is too much water. So you should, it's a radio contest. It was awful. Long time ago, before you lived. So, okay, just to review, hypertonic is a solution that has a higher concentration of solutes. Solute is the thing there's less of. So we have salt and water. The solute is the salt, the one there's less of. The water is the solvent. When we add those together, they make the solution. So a solution, meaning salt and water, contains way more solute than inside the red blood cell. And so the water goes out of the cell to try and make the concentration the same. Isotonic means it's the same on the inside as the outside. That's where we operate in a healthy place. There's no net osmotic flow, no change in the cell. Hypotonic means that the solution has less salt than inside the cell, and the water will go in the cell and the cell expands. So important to drink water, not too much water. Okay, so what we've been talking about is osmosis. So osmosis is, again, just movement through a semi-permeable membrane. And so, for example, let's look at, like, this is our semi-permeable membrane right here. So here's seawater, here's just water. Seawater, and then normal saline, like our body's like 9% weight volume. So much lesser, I think seawater is like 17% or something. Okay, so seawater has much more salt ionic compounds than normal saline does, right? And so these two chambers are separated by this semi-permeable membrane. So initially the volumes are the same. See, so initially these volumes are the same, but over time, the volume of the chamber containing the normal saline right here, so there's just our normal saline, decreases, and the volume of the seawater increases due to the migration of the water molecules through this membrane. Right? So again, it's trying to get both of these to have the same concentration, and the only thing that can move through is the water. And so the water, so this one had a lower concentration of salt. This one had a higher concentration of salt. It wants it to be the same. So all the water can do, if the water moves this way, it's going to decrease that concentration, right? But the only thing that can do is the water can move through. So this pressure or this volume increases. This difference, that's what we call the osmotic pressure, right? It's the pressure difference created by this movement through a semi-permeable membrane. Okay, so how do we use this? So again, what is osmotic pressure? Again, it is the pressure applied across the semi-permeable membrane to stop the flow of water from the compartment containing pure water or a less concentrated solution to the compartment containing a more concentration solution. And we can use this equation right here. This weird thing is called osmotic pressure, where P, so sometimes they just call this a P because a lot of times people don't do this, so they just call it P. So P or pi, big pi, not 3.14 pi, and we have to stop using the same. We have to stop using the same symbols that mean different things. So the P or the pi is the osmotic pressure, different than pressure of a gas. Okay, it's different than pressure of a gas. M is the molar concentration or the molarity. R is the gas constant, same thing, 0.08206. And T is the temperature. And so the connection between osmotic pressure and pressure exerted by the ideal gas is very similar. It's just N over V becomes RM, our molarity, because moles over volume. So it's very similar to PV equals nRT. It's just adjusted a little bit. And so again, this is molarity. Remember, we've talked about this. Molarity is moles over liters. We talked about that at the beginning of the semester. Oops. So again, we're focusing on the movement of the water, solvent. Remember, the solute is the one there's less of. The solvent is the one there's more of. Water's what we call the universal solvent. Okay, so, and then we're going to talk about these colligative properties in just a minute. Colligative properties are properties that depend only on the concentration and not the identity of what's in the solution. And so we're going to talk a bunch about that maybe today. Okay, so let's practice with how we use this. So remember, it's the big pi equals molarity times R times T. You don't need to memorize this equation. I'll always give it to you. So if the total concentration of the solute particles in the fluid is 0.310 molar, I'm just going to put this right here so I can write it better, MRT. So our molarity is 0.310. And remember, molarity is moles over liters times R use these 0.08206 liter atmospheres moles K. Again, you can use 0.0821, I don't care. And then 37 plus 273 is 310 Kelvin, right? I think so. I'm not sure. So just to prove to you these units, moles, liters, temperature, atmospheres. So you indeed end up with atmospheres. So what is the pressure in this case? And I'm pretty sure I have this here. Oh yeah, here it is. 7.89 atmospheres. And so that's a lot of pressure because we're at 1 atmosphere, right? So think about that one. So this is like the same amount of pressure in like a bike tire, right? And so it's not a small amount of pressure. So if there was no opposing pressure, water would migrate across the semi-permeable membrane of the red blood cells if it were to be immersed in distilled water, causing the cell to swell up and eventually burst, right? So, okay. So by the way, this is why you're not supposed to drink distilled water, because we need, like our bodies to live need salts. So if we drink water like tap water or even in bottled water, you'll see. So we all drink bottled water. Look on the side of your bottled water. It'll say bottled water, and then it'll have like potassium chloride or potassium nitrate. Those are salts, ionic compounds, because our body needs salts because we need to keep the concentration on the outside of our red blood cells the same on the inside. If we drink distilled water, there's no salts. Distilled water is the same thing that we have in lab, deionized water, which means deionized means it took all the ions, all the salts, all the like NAs and CLs out of the water. If you only drink that, then you're going to create a hypotonic solution. And eventually you'll have not enough salts on the outside of your cells. And so the water will migrate into your cells and burst. So note, don't drink distilled water. Okay, if you drink it once, it's fine, but people should not drink distilled water. And again, look on the side of your water bottle. It has salts in there because we need salts to live. Okay, now let's look at another one, molar mass. What is the molar mass of a protein if 5.87 milligrams, oh, look at that, another metric conversion, per 10 milliliters gives an osmotic pressure of 2.45 torr at 25 degrees Celsius. Oh, doesn't that one look like super fun? Okay, so here's what we have, and we want molar mass. Remember, molar mass is grams over moles. Okay, so let's see here. So we have our formula, right? Which is again, I have it written here for you. There it is. See, I couldn't make my P work better. So this is like, that's our pi. Pi moles per liter RT. And we want molar mass, right? So we've got a milliliters and a milligram. So we're definitely going to need to get rid of those. And we want molar mass. So we need grams over our moles, right? So what do we have here? So we have the osmotic pressure. So I'm just gonna do this. Pi equals molarity times R times T. Well, we have a temperature. We always have R. They're giving us this. So we can solve for molarity, okay? All right, let's just try that first part. Let's just go there first. So important here, look, oh, they gave us a torr. Remember, whenever we use R, it needs to be atmospheres, liters, moles, and Ks. So that has to go to atmospheres. I don't even know what that is. 2.45 torr. And again, 760 torr in 1 atmosphere. I don't think I did this one because I don't remember. Usually I remember. So 2.45 divided by 760, 0.003224, close enough, atmospheres. Right, so when we solve for this, our molarity is going to be our 0.003224 atmospheres. Right, so I'm just going to rearrange this. We end up with molarity equals pi over RT over R 0.08206 liter atmospheres mole K times our temperature, which is, what is that, 293? And that should give us our 298. I can add. It's 298, thank you. 298. Right, and so that should give us our molarity. So what do we get? Oh, I shouldn't have deleted that point. 3224 0.8206 times. This is why I always do these before. So I got 1.3 attempts and then I get 4. Is that right? I think I did this here. Yep. I got 1.3 184. I'm just going to keep more than I need times 10 to the negative 4. And again, this is molarity, so it's moles over liters. Okay, but we want molar mass. Okay, so what do we do now? So we get our molarity here. So I'm going to erase that. Everybody got their molarity? I wrote it pretty slow. That's our molarity. Same thing. I just set it up differently when I did it this time. It's the exact same thing I just did. I just did it all in one piece, just to make it a little easier. Then, oops, I'm out of room. So then we can get to our moles. Again, how do we get to our moles? Well, we got this, right? And we have molarity, and we have our milligrams. I'm not sure these are milligrams, but this can help us get to moles, right? Because remember this, molarity is moles over liters, right? So therefore, remember this, liters times molarity equals moles. So we can get to our moles, and then we can get to our grams, right? So here's our volume. We just need to convert that to liters. 10 milliliters, 1,000 milliliters in 1 liter. Or you can do what I do. I just say 10 times 10 to the negative 3 liters. I just put 10 to the negative 3 in there. Makes my life so much easier. There's my volume. Then I just use our molarity, which is right here. And that's going to be 1.318 times 10 to the negative 4 moles over 1 liter. And that's going to give us our moles. Molar mass is grams over moles. I just served my moles. That will be my grams. I just have to convert it, right? So this, remember, we did this a bunch at the beginning of the semester. So when I solved it here, I did it a little bit differently, but sorry, I kind of ran out of room on this problem. So here, I just used a different conversion. Some of you like to use this conversion. I'm not a big fan of it. I used to do this. Now I say there's 1,000 milliliters in 1 liter, but this one doesn't even work. This is the wrong conversion. 1,000 milliliters. I should fix that. 1,000 milliliters in 1 liter. Here, this is our molarity that we got from using our, sorry, right here that we got. And now again, this is our moles. Molar mass is grams over moles. This can't stay here like that, right? It can't stay here like that. We need to change it. It's milligrams. So remember milli? Maybe not. 5.87 milligrams. There's 1,000 milligrams in 1 gram. So that ends up being 5.87 times 10 to the negative 3 grams. So our molar mass is going to be 5.87 times 10 to the negative 3 grams over 1.318 times 10 to the negative 6 moles. I don't know what we get. I'm not sure if I did this piece. Okay, questions on this one? Let me see if I did this. Oh, I did. Let me just erase this because here it is the same, almost exact same thing. And this is our molar mass. Questions on this one? Okay. So this one took a lot more thought, but I wanted to make sure that we did a nice hard one because you're going to see some of these on your Chem 101. Okay, next piece. We're bringing back, so we brought back our molarity that we learned at the beginning of the semester. Now we're going to bring back our electrolytes that we learned at the beginning of the semester. So do you remember weak and strong electrolytes? Remember, an electrolyte is anything that conducts electricity, or when it comes apart, it makes ions. So remember we say like all ionic compounds are electrolytes. So like NaCl, when we put it in water, becomes Na plus Cl minus. Anything that makes pluses or minuses, those are electrolytes. So a weak or a strong electrolyte, remember strong just means 100% comes apart. Weak just means less than 100% comes apart. So remember we learned this at the beginning of the semester. So we're talking about our electrolytes. We're pretty much going to be talking about strong electrolytes now. So weak or strong electrolytes, 1 mole of it produces more than 1 mole of particles in solution. So the value of the molarity is greater than the concentration itself. And so like, for example, I'll just write in blue. I was going to hopefully change this, to yellow. I think you will be able to see it better. So NaCl. So when we have NaCl, when it comes apart into 2 things, right? What if we had MgCl2? It comes apart into 3 things. It comes apart into an Mg2 plus and a Cl minus. Remember when we did dissociations at the beginning of the semester? And another Cl minus. So this comes apart into Mg2 plus 2 Cls. This makes 2 things. This makes 3 things. That's what we're talking about, how the value of the molarity is greater than the concentration because it breaks up into multiple parts. Now, a Van 't Hoff factor is the ratio of the concentration of the solute particles in a solution to the concentration of the particles that would be there if the solute didn't dissociate. And these are all determined experimentally. So when a solute is a weak or strong electrolyte, 1 mole of it, so 1 mole of this, becomes more than 1 mole in solution, right? And so this is mostly, especially with strong electrolytes. And so these are called these Van 't Hoff factors. The actual ratios are called Van 't Hoff factors. So for example, the Van 't Hoff factor for NaCl, we would say is 2. The Van 't Hoff factor for MgCl2, we would say is 3. Now that's if it is perfect, but it's really not perfect. So let me just show you these really fast. So I don't have NaCl, but here's like MgCl2, right? So this comes apart, or sorry, CaCl2 is like MgCl2. This would come apart into Ca2 plus and 2 Cl minuses. So 3 things. So we would expect that it's 3, but actually experimentally, we found it's 2.4. Let's do this one. So this would come apart into 3 Na pluses. Again, this is like those dissociations we did at the beginning of the semester, and 1 PO4 3 minus. So that's 4 things. We would think, oh, it's 4, but experimentally, it's actually 3.1. Here's our NaCl. Remember when we said this would come apart into Na plus and Cl minus? That's 2 things, but it's actually 1.9. Okay, so why is what with the theoretical not the same as the experimental? So when we have concentrated solutions, the cations and anions don't completely dissociate. What does that mean? So sometimes we make clumps. So we think when we put salt in water, we get Na and Cl, and they separate. Well, most of them separate, but some of them are like, no, but I don't want to. And so they stay together. So we don't get 2, we get a little bit more than 2 because they don't behave as independent particles. Sometimes they cluster together, right? Now, interesting one here, look at this one. This is a great question. If you can remember from the beginning of the semester, this one, experimental and theoretical, are exactly the same. Why? Because this is a covalent compound. Covalent compounds don't dissociate. Only acids and bases and ionic compounds, right? Ionic compound, ionic compound, ionic compound, ionic compound, ionic compound, covalent compound, right? So if you put, how can you tell if it's covalent? two or more nonmetals. Okay, they do not come apart. So when you put ethanol in water, do you know what you get? Ethanol and water. That's what you get, right? Literally what you get, ethanol and water. It doesn't come apart, right? These are all ionic compounds. Metal, polyatomic ion, metal, polyatomic ion, metal, nonmetal, metal, polyatomic ion, metal, nonmetal, right? So ionic compounds only come apart. Molecular compounds or covalent compounds do not come apart. Okay, so we can use this. This is our Van't Hoff factor. This I, it's the number of things it breaks apart into. Now, if sometimes, just to let you know, sometimes they'll give you the actual Van't Hoff factor. So in Chem 101, it'll say like, here is the Van't Hoff factor, use this. But if they don't, you use the number you can best remember, right? Like this is 2 plus 1, that makes 3. But if it says, hey, here's the actual Van't Hoff factor, use the one they give you, right? And so Van't Hoff factor is this I. And so we just add it into our equation. So like, for example, this one, a 47 milligram sample of water-soluble non-electrolyte. Non-electrolyte means it doesn't come apart. That's a molecular compound. From South African tree, the sample is dissolved in enough water to make 2.5 milliliters of a solution. The osmotic pressure is 4.89, and here is our temperature. What is the molar mass of this compound? Okay, so we know the concentration of the solution is going to be, right, moles over liters. And so we need to figure this out. We need to find our molar mass. And I don't want to just give you all the answers. So when we do this, right, we have our formula, pi equals mRT, and we want to know our molar mass. We have this, we have our temperature, we have our R. So we just solve for our molarity equals our osmotic pressure, our giant pi, and then IRT. But again, I is just going to be 1, so I'm just going to ignore it because it's a non-electrolyte. So then I just plug this in. So 4.89 atmospheres over R 0.08206 times our temperature 298 K. That's going to give us our molarity. Remember, molarity is moles over liters, right? And then look, they give us this liters. We can use that whole molarity piece. Okay, so when we do this, we get, I'm just going to put your answer here. Here's your molarity, right? So this is our molarity, and 2.5 milliliters. Remember, sorry, I'm trying not to go over. Molarity times liters equals moles. Our volume was 2.5 milliliters. 2.5 times 10 to the negative 3 liters times our molarity. 2 times 10 to the negative 2 moles over liters. This is going to give us our moles, which ends up being 2.5 times 10 to the negative 6 moles over our grams, which I don't remember what they are, so I have to go back. 47 milligrams. 47 times 10 to the negative 6 grams. Okay. And so then we end up with 9.4 times 10 to the 2 grams per mole. Right, so a little bit different. There's another way you can do this too, but I'm not going to do it this way. Let's just do it the way we've always done it, with our molarity and our unit conversions. Okay, so I went exactly, sorry I had to go kind of quickly at the end there, but I went a little bit fast at the end. But again, same kind of things we've been doing. We just added in a new piece here, osmotic pressure. And again, you don't need to memorize this new conversion or this new formula. I'll always give that to you. So we're going to continue this